Yes, you see here the subject of my talk and my co-authors. My co-authors are Professor Bolotnik and Dr. Figurina from our institute. So this is the contents, and after short introduction, I will consider two kinds of systems that can move in a resistive medium. First is a frog-like or fish-like systems that have a link attached to it, and by vibration of these links, the body can move progressively in the resistive medium. And the second system is a system containing an internal movable body. And due to the motion of this inner body, the system also moves progressively. So the first model is, you can see here, it consists of a main body here that can move, that is symmetric and can move progressively along the x-axis, and two links are attached to it, OA and O prime, A prime, and they are always symmetric with respect to the x-axis. So the angle phi and phi prime are always equal to each other. And we assume that there is also, the resistance forces also act on these links, but we will, for simplicity, admit that the resistance force applied to the links is applied really only to endpoints, A and A prime. And these links are considered to be massless and they have no resistance. So mass of the main body, this is added mass of the body in the liquid, and length and angles, angular velocity, and so on. So we assume that the motion of these links is periodic, with period T capital. Another model is a fish, which have, instead of two legs, it has only one tail, and this tail moves periodically, but it has the following symmetry property, that after a half period, angle phi has negative sign, and it is mirror symmetric with respect to the motion of the first half period. We can see that under certain simplifications, these two systems can be described by the same differential equation. Here you see many some models of fish-like robots from MIT. And here the equation of, to derive the equation of motion, we first calculate the velocity of the end point, velocity of the point A, and the resistance force applied to A is quadratic, as you can see here, and directed against the velocity of this end point. So the equation of motion, after certain simplifications, is presented here. This is mass and added mass of the main body. Here you see the resistance of the main body proportional to the square velocity. We assume that this velocity of the main body does not change its sign. It is always positive. And there are the forces applied to the endpoints. And due to symmetry, they are equal. These projections are equal to each other. And after simplifications, you see that we have this equation. And note that these coefficients C and K have the dimension of inverse length. It can be explained by the following simple example. If we consider a motion of a mass under the quadratic resistance, The equation is shown here, and if we integrate this equation and find the velocity as a function of distance, not of time, but of distance, then it is exponential. This exponential formula. So C is just inverse length where the velocity decreases by the vector of E. We assume that the resistance of these links is much smaller than the resistance of the main body. So epsilon is a small parameter, and the equation then is simplified again. You see it here. And now we can use the averaging procedure, asymptotic method of averaging by Pogolubov and Tropolsky. Then we must, to use it, we must average the right-hand side of this equation over the period, which is equal to 1 after normalization. And here you see this equation shown here. I capital is this integral. So to find out the equation in explicit form, we must prescribe some time history of the angle, and of course angular velocity as its derivative. Then find this integral I capital, and then we have a very simple differential equation. Note that if this I is positive, then the right-hand side is always negative, the velocity decreases, and at last the body stops. It is not an interesting case, of course, where the resistance is higher than all propulsion that can be created. A more interesting case is when I capital is negative, and then this equation has a stationary solution, which is globally asymptotically stable, of course, in this case, and equal to square root of minus I. And in this case, the velocity tends to this V star. So we will calculate the V star and try to optimize it, to maximize the velocity of the motion.
Can I just ask a technical question?
Excuse me?
Can I ask a question?
Yes, please.
Have you assumed that the velocity of shaking is substantially higher than the translational velocity of the fish?
Yeah, we have high frequency vibration of these links.
But high frequency times the radius is bigger than the...
Yeah. So all exact estimates are given in the paper. So it is, of course, it is omitted here in this presentation. So the first and simplest time history of the angle is piecewise constant angular velocity. So first we increase our angle from 0 to some given positive value phi 0, and then decreases. So deflect and then retrieve our links. So this is the analytical expression where omega plus and omega minus are angular velocities of deflection and retrieval. And if you calculate this integral, we find this simple formula. And you see that if the angular velocity of deflection is higher than the angular velocity of retrieval, then we have positive I capital, and then the motion with positive V is impossible. And more interesting case is when omega minus is higher than omega plus. You can see here the picture corresponds to this case where omega minus is higher. This is more steep part of this time history, and then there is stationary velocity. So the first conclusion that you must deflect slower than retrieve, and every one of you who swims knows that we move in the same way when we swim by breath style, and the frog also, its angular velocity of deflection is slower than very high angular velocity of retrieval. Of course, for a frog, we have also another link, and another joint at the knee. But nevertheless, the general picture is as I told you. At first, I spoke about only drag applied to the endpoints, but also if we consider this endpoint as a fin, which has some, for example, rectangular shape here. You see here the view in vertical plane, and then besides the drag, we must take into account the lift force, which is produced by this small wing, small fin. And then these forces may be also taken into account. And here are some parameters, and these are results of simulation. Then you can see that the taking into account of lift always increases the average velocity. So taking account of lift also leads to higher average velocity than the case without lift. Here also the same picture. You see here average velocity versus angular velocity of deflection of the tail. And here average velocity versus angle of deflection. It is here about half radian, 30 degrees, for example. Average velocity versus relation. Omega 2, it is omega minus, corresponds to retrieval. Omega 1 corresponds to deflection. So we considered before piecewise linear time history of the angle. But now let us try to find optimal time history of this angle phi. So we here consider optimal control problem under the following assumptions. The omega is bounded from below and from above, and maximum of the angle phi is prescribed, and then our integral is presented here as a sum of two integrals. This is for deflection, this is for retrieval, and we want to minimize this I, and it leads to the maximum value of the average velocity. So the problem is reduced to two independent problems. The first one for deflection, the second one for retrieval, with corresponding boundary conditions and different constraints. For deflection, we have positive angular velocity. For retrieval, negative angular velocity. And the result, this optimal control problem is solved analytically, in an explicit way, using Pancreatic maximum principle. I will only here show the final results. There are some publications that correspond to this paper, and we can find all the calculations here. The final result is as follows: that the period consists of three intervals. On the first interval, from zero to t star, we have maximum angular velocity of deflection. Then comes the interval where the angular velocity changes. And then the last interval, we have maximum angular velocity of retrieval. And this interval, sometimes it doesn't work. We have here the equation which describes the omega as a function of phi, and by integrating it, we comes to these results. So to find the solution, we must first solve this transcendental equation for z. You see that all other values here are given, including theta, which is also defined here. And so this equation, it is shown, has only one solution in this interval. We find the value of z, and then this is the implicit formula that describes phi as a function of time. And our maximum average speed is given by the last line on this slide. Now you see here some examples. This is the rather short first interval where we have linear part, then we have changeable part. This is angle, this is its derivative, this is omega. And then we have retrieval with maximum possible angular velocity. This is another example. Also three intervals: interval of maximum, interval of maximum negative angular velocity, and some intermediate part. Note that, for example, here we have maximum velocity of translation given by this number, and this can be obtained for piecewise constant angular velocity. The example that was shown first on previous slides. So another system, another model. I told you that we will consider two kinds of systems.
Do you have another question?
Yeah, please.
Some intuition about why the recovery has two phases instead of one simple phase?
We have first
opening and then closing,
deflection, and then retrieval, which must be as fast as possible.
But the opening, you said, breaks into two intervals.
Yeah.
Why? What's the difference?
It's not so easy to find. I cannot give explanation on fingers. It's more complicated. Non-linear optimal control problem, so we must not be ready to explain it very soon. Another another mechanical system is a body with internal mass. And if the first system has a biomechanical analog, as we speak about fish and frogs and so on, and even then, and here we have no exact biomechanical analog, because here we assume that this mass moves inside the body. It is not. It must be separate from the body. We can assume that this is a boat which moves in a fluid. There is no oars, and some person sitting in the boat can only move forward and backward in the boat, and he or she must produce average motion, translation motion of the boat. Equation of motion is shown here. This is acceleration, x double dot is acceleration, relative acceleration of the internal mass with respect to the main body. And this is the resistance force, which depends on the velocity of the main body, which is given by x. X dot is its velocity, x is absolute displacement. And this function here we consider as a more general type of this function. It is twice differentiable and monotonically decreasing function of velocity. Of course, it must be directed against the velocity, so its work is negative, of course. It is resistance. We assume that the motion is, we consider periodic motions. main body with periodically changing velocity, excited by a periodic motion of the internal body relative to the main body. And period t is prescribed, and this is the condition that guarantees that we have no displacement, that our displacement is bounded inside the body. Optimal control problem. Let us also state optimal control problem. For this system, we are to find the optimal control, the relative acceleration of the internal body bounded by absolute value that maximizes the displacement of the main body over the period, subject to boundary conditions, periodicity boundary conditions. Non-dimensional variables are introduced, and after some simple change of variables, we have this normalized problem. We have one equation with nonlinear function, given nonlinear function of a rather general type. This is control bounded by unity, its absolute value is bounded, and this is the displacement. This is the displacement which must be minimized because we have here negative sign. And periodicity boundary conditions. Several words about the class of functions R of V that we consider. First, we assume that the derivative of this function R of V is non-negative, and there is no interval, no linear interval. So R double prime of V is not equal to 0 on any interval. It can be only equal to 0 at some points. And then there exists an admissible control that produces a non-zero shift of the main body for the period. As a corollary, if the function is odd, the function R of V is odd, then there exists an admissible control that produces a positive shift of the main body for the period. Now, what class of function R of V? This is a rather complicated definition, but it is written here. The function belongs to class R if for any tangent to the curve R of V at a point at which this curve is convex downward, there do not exist 2 points, two points of intersection of the curve and the tangent, one of which lies to the left of the point of tangency and the ordinate axis, and the other lies to the right of the point tangency and ordinate axis. Here you can see an example. This function R of V, it goes for this 0 point, and it is monotone, and here you see it is admissible function. It belongs to class R capital, and this function do not belong. So, rather exotic case, I don't think that it is so interesting, but here we consider more general case as quadratic and a more complicated case of resistance force as a function of velocity. Now, for this general class of functions, we find the optimal control consisting of 4 intervals. 2 intervals correspond to the maximum and minimum acceleration of the internal body, +1 and -1. And 2 intervals to another intervals correspond to the changeable u of t. Intermediate values of it. And here the velocity is fixed. It is v plus and v minus. So either the acceleration is constant or the velocity is constant. We will see here this on this picture. Excuse me. If the function is convex upward, then the optimal motion does not have singular segments. So here we have, instead of 4, we have only 2 intervals. And for more interesting case, where the function R of V, you see here, for example, to this class belongs all functions that are powers of V, quadratic and more general, where alpha is larger than 0 and not equal to 1. Then, for this case, the function R of V is odd, and here the solution is presented here. It consists of 3 intervals. For 2 intervals, the acceleration is constant and maximum and minimum. And here the velocity changes. And for the singular arc, the U of V is intermediate, has an intermediate value. And here the velocity is constant. So either the velocity is constant or the acceleration is constant. Here, this is the result of this. This is another example. So I can come to an end. The first conclusion that a body with 1 or 2 links attached can move in a resistive fluid with quadratic resistance forces. The forward motion is possible if and only if the angular velocity of the retrieval of the links is greater than the angular velocity of the deflection of the links. That I have proved. The average velocity is higher if the tail is subjected not only to the resistance but also to the lift force. Optimal control of the links attached is obtained that corresponds to the maximum average velocity of the system under the constraints imposed. Now, optimal control for the body with an internal movable mass is obtained for periodic motions of the internal mass in resistive medium. The structure of the optimal control is determined for a wide class of resistance forces. It consists of not more than 4 intervals and sometimes 3 intervals, and sometimes even 2 intervals. But we have indicated how many intervals are in each case, and we give equations to obtain the lengths, the durations of these intervals. For quadratic resistance forces, optimal control consists of 3 intervals, including 1 singular arc. So, as I have already mentioned, the first kind of systems, the systems with links, it imitates the motion of some animals and fish. And the second example, vibrationally excited motion, has not direct analog in biology. We have some experimental results in our laboratory. I did not include them there, but I have shown them at some other meetings. And for example, we have for the second model for the body of with internal mass, we have such devices that can move inside a tube due to high frequency vibrations of a mass inside this vehicle, inside this capsule. And this capsule can move in a tube of 1, 2, or less than 1 centimeter diameter. I think that these modes of motion, the motions without legs, without wheels, they can be of interest for different robotic systems. Thank you for your attention.
Do you have a question? I have like 10 questions, but other people should ask.
you start.
Okay, first off, this is not a question, but just a comment. There's a beautiful song in Swedish, and the words to the song are, "Who can row without oars?" There is a beautiful song in Swedish, and the words to the song are, "Who can row without oars?" As Professor Chernousko can row without oars, should be the answer to the song.
You must move the boat in the correct way.
I sent you a link for the song. It's a beautiful song. You put up there alpha not equal to 1. You wrote for the second problem alpha not equal to 1. I know, because I know that alpha equals 1, you cannot move.
Yeah.
But does your mathematics...
Yeah.
When you're trying to do the optimal control...
I have proved, of course, that for alpha equal to 1, there is no possibility of translation.
But there's a separate proof, separate from optimal control.
Yeah.
But when you do the optimal control, do you run into trouble when alpha equals 1?
We know that if alpha is equal to 1, then the body will only oscillate about some center. So progressive motion is not possible. Of course, we know that. We have proved it in different way. It is very easy to prove. It can be proved in 1 or 2 lines. Of course, you know that. And so, of course, optimal control problem also produces the same result, of course. But there is no contradiction here.
No, it's not a contradiction. I just imagine you would get lost in the math.
No, it is, of course.
Okay, and I guess my last question is, I don't distrust your math. Your math, I guess, is correct. But do you ever just throw your problem into optimal control software package and see what the software gives us an answer?
You see, the problem is solved in 2 stages. First, we make some analytical, we elaborate analytical equations, conditions of optimality, and then we solve numerically those differential equations. So, of course, we use computers here. It is not only analytical solution. Some nonlinear equations we must solve and integrate. Of course, we use it.
But you could just throw the problem into the computer with very little analysis.
Yeah.
You don't ever do that, though.
We didn't do that because we have found some integrals.
You trust
Why should we make a computer do our work for us?
So, sort of one question and maybe a bigger picture comment. So you did a control to try and get the object to move as fast as possible, and you talked about controlling it subject to also not keeping some kind of work done small, So you optimize the motion, you maximize the motion subject to not using too much power, for example, in the motion of the entire body. And the other comment is that this is essentially an ordinary differential equation that you're controlling with a certain assumption about the resistance of the fluid on the body. I guess one question you could ask in terms of Friday's discussion, the big picture, is to what extent do these ODE models, are we happy with them in terms of modeling the actual fluid forces? So for a Stokes flow, we'd be happy for a sphere, or asymptotic results for a long rod. For a very high Reynolds number, you might be happy with quadratic drag. How well are we doing with intermediate Reynolds numbers with these kinds of fx in one direction, v squared? So that's kind of a big picture question.
Yes, I understand. The first question and comment is that here we assume only that we are interested in the speed, and we do not count on energy losses. Of course, this is one-sided approach. For a transport vehicles, it is important not the coefficient. It is important the energy, like for cars, energy per distance, and this is another performance criterion that must be taken into account. So for some we have been worked on these problems for several years already, and here are only two newest parts of our research. But we have also considered this case. We can try to follow two optimal performance criteria. One is speed, and another is energy loss or work per unit path. And on this two performance criteria, we find Pareto optimal curve that shows how much we lose if we make it a bit quicker, but then we lose in energy. So some results of this kind are also available. So we also think about it and take it into account. But here I did not touch this. And the second, of course, our resistance assumptions are very rude. We just assume that we have only a simple formula depending on velocity. If we consider a body moving in a fluid, we know that there are a lot of vortices and many other things, and hydrodynamics is, of course, much more complicated. But for some cases, maybe this will be considered as a starting point. I'm sure about it. For example, for the case that we considered for a capsule moving in a tube, it is quite enough, because when the capsule moves in a tube and inside, due to electromagnetic force, there are very high frequency vibrations of mass, then the friction between this capsule and the tube consist of dry friction and a bit of linear friction. So for some cases it may be enough. And it gives you some idea how to start with these problems. This is my answer.
Do you have another question or comments? Thank you very much.